Drones are rapidly becoming the backbone of our critical infrastructure, inspecting power grids, delivering medical supplies, and handling national security reconnaissance. But they share a massive, invisible flaw. The wireless command signals controlling them can be spoofed, hijacked, or jammed right out of the sky. Currently, we secure those airborne command links using public key cryptography. We shield the data behind the computational difficulty of specific algorithms, equations that would take a standard computer thousands of years to brute force. But that defense is time-limited. Within the next decade, large-scale quantum computers will possess the processing power to solve those algorithmic problems in a matter of hours. If an attacker intercepts an encrypted data stream today, they can store it and decrypt it as soon as the technology matures. A compromised drone network is a permanent breach of a critical national asset. As long as we rely on the computational limits of current hardware, our airborne networks represent an escalating and ultimately indefensible vulnerability. The solution requires abandoning math for the laws of physics. It's called quantum key distribution. Instead of an algorithm, the cryptographic key is encoded into the physical properties, like the polarization, of individual photons. According to quantum mechanics, simply observing a photon detectably alters its state. If a hacker intercepts the stream midair, the photons physically change. The receiving system identifies that change, flags the interference, and aborts the key generation. Because the information is tied to a quantum state, the transmission is theoretically unhackable. We already use this technology on the ground. When you fire single photons through the dark, vibration-isolated environment of a buried fiber optic cable, the quantum link remains stable. But trying to maintain that delicate subatomic link between two shaking, fast-moving drones in broad daylight is a different matter. The stability of fiber optics doesn't exist in the chaotic reality of flight. To successfully transmit a quantum key through the air, you have to hit a moving drone's optical receiver with a single photon over a distance of several kilometers, while both platforms are in flight. The drones themselves generate extreme high-frequency vibrations from their own motors, creating a constant internal threat to the signal. At these distances, if the transmitting laser drifts by even a fraction of a millimeter, the microscopic quantum signal misses the target entirely. To stabilize the beam, engineers use a custom pointing, acquisition, and tracking system, or PAT. This mechanical countermeasure is mounted directly onto the drone's chassis. This schematic outlines the first layer, the outer loop. A motorized two-axis gimbal handles macro movements, tracking the receiver across a wide field of view to compensate for sweeping changes in the drone's flight path. Inside that assembly sits the inner loop. A fast steering mirror, guided by a position-sensitive detector, makes 800 micro-adjustments per second to counteract high-frequency motor vibrations. By layering these dual mechanical stabilizers, the system decouples the fragile subatomic signal from the airframe, allowing it to lock onto the target. Once the laser is successfully tracked, a second obstacle remains: the sun. Background photons from daylight can easily drown out a single quantum particle. Engineers utilize specific light wavelengths, like 1550 nanometers, which have natural daylight resistance. This is paired with strict spatial and temporal filtering. These filters act like microscopic blinders at the receiver. They ensure the system accepts only photons arriving at the exact correct angle and the precise correct microsecond. Finally, the speed of the aircraft creates a Doppler shift. When a drone flies towards a receiver, its velocity compresses the incoming light waves, which ruins the phase matching required to decode the data. To solve this, the receiver uses continuous frequency calibration. Adaptive algorithms measure the velocity of the drone in real time and mathematically realign the compressed waves back into a readable phase. Successfully transmitting an airborne quantum key requires defeating both the sun's radiation and the physics of relative motion. These engineering feats have taken the technology out of the lab. Teams have achieved kilometer-scale daylight QKD links between flying drones and moving ground vehicles. This proves a single connection is possible. The next step is scaling those individual links into a reconfigurable network architecture. This map illustrates a trusted node configuration. Here, individual drones act as secure relays, where one drone receives a quantum key, decrypts it internally, and passes it to the next drone in the swarm. Alternatively, in an untrusted node setup, the drone acts as a physical mirror in the sky, bouncing the secure photons down to a ground station without ever decrypting the data itself. These aerial swarms act as the critical last-mile bridge. They can establish immediate, ad hoc connections in contested environments, linking ground-based fiber networks to global satellite constellations. By conquering vibration, light, and motion, drones have evolved from security vulnerabilities into the ultimate secure routers, anchoring the future of an unhackable global quantum internet.